Hello everyone, and welcome to MakeLearn 360. In this video, I'm going to teach you a cantilever beam with UDL or uniformly distributed load. So how can I solve this problem? Let's go straight forward. You will just try and section here, and then you will draw what you have gotten. So this is like a section, okay? Let's call it section XX. Now, you realize that there is this sort of uniformly distributed load here, meaning that if you take the section, still there is this uniform distributed load here still occurring, okay? And then for uniform distributed load, it will act like as though it's like a rectangle, okay? So the intensity here is like W, which is like acting across. All right. So again, if I want the actual, if I want the actual W, which is acting, then that one is going to be, how do I put it? If I want the actual, the load, then I'm going to multiply this load by the length. So for this one, if I take X like this, a section X here, which I took, then we are going to say that the load due to the UDL is going to be the W times X, and then it will act exactly at a point. So it's going to be W times X, where W is the load. It's going to act at a point halfway. So let's call that distance say X divided by 2. Okay. All right. So right now we are done with this part. And then one thing that we also have to take notice of is that whenever you do this, you have to bring something which is very important. All right. So one thing that you have to realize is that there is this rule here that we have to follow. Okay, so you are going to bring the shear force V down, and then a moment which is going this way. Let's call that moment mx. Okay, now at this juncture we have this, so we are going to sum moment about x, and let's say that clockwise is positive, should be 0. If we do this, then we are going to get so we are going to sum moment. Okay, we are going to sum moment. So summing moment, what do we have? So we will get this wx is going in a anti-clockwise way, so it's going to be minus w multiplied by x, and then the moment distance is x over 2. However, the moment which is already there, the mx, is going in the it's also going anti-clockwise, so it's also going to be minus, should be 0. All right, so from here we can write that mx is what? Minus wx squared over 2. So once we've been able to achieve this is the moment that we want. But we can also use another method to get the moment. We can use the shear force to get the moment. So we can sum forces. Positive in this direction should be 0. If we sum up the forces, we have minus ws, which is coming down, and then we have minus v, which is also coming down to be 0. So in other words, v is equal to minus wx. So from here we know that moment mx is given by the integral of shear force. If we integrate shear force with respect to distance, we get moment. So let's integrate the shear force. It will be minus w x, the integral of x is going to be x squared over 2. You see, this is also the same as what we got here. So either you use the shear force to get the moment, or you sum moment, you get the same results. Now that we have been able to get the moment, we will go ahead and then use the equation, which is EI d squared y dx squared should be what? Minus wx squared divided by 2. Okay. Once we've been able to do this, then we just have to go straight forward and then get our deflection and our slope and then our deflection. So if you integrate this one, you are going to get the slope. So it's going to be minus w over 2. What is the integral of x squared? It's going to be x cubed over 3. Then we add a constant c1. Okay. Now, there is one thing that I want you to be aware of. Whenever you take a cantilever beam, for a cantilever beam, all the time at the fixed end like this, the deflection will be 0 and the slope will also be 0. That is always special for a cantilever beam. So let's say that this point is x equals 0 and then this section is x equals L. All the time for a cantilever beam, the fixed end, the deflection is 0, the slope is also 0. So in fact, the deflection is going to be something like this. The deflection, let me bring this one down. Okay. For a cantilever beam, always the deflection will come this way. All right, it will come in that sense. So there will be no deflection here, and then there will be no slope. But the maximum of the deflection for a cantilever beam is going to occur at the free end, and that is what we call Y max. I hope the concept is clear. So meaning that the deflection will be coming like that, but the maximum deflection will be experienced at the free end. Okay. So that is it. Now let's try to solve for C1. So at x equals L, which is the free end, dy dx, at the fixed end, the slope is 0. That's what we said. So it means we will have EI 0 equals minus w over 6. Then we'll multiply it by x cubed, which is L cubed plus C1. Therefore, we can say that C1 is what? W over 6 L cubed. Then we will just substitute the value of C1 back into the equation. Now, if we do that, then we will get what? EI dy dx is what? Minus w over 6 x cubed plus w over 6 L cubed. All right. So, in fact, what we have right here is our, slope equation. So this is our slope equation. Slope equation. Let's try to find the maximum slope. Now the maximum slope, in fact, the maximum slope will occur at the free end, because you see that the slope is coming here, and then as it's moving up, it becomes more steeper. So the maximum slope will occur at the free end. So for a cantilever beam, at the free end, the maximum slope and then the maximum deflection will occur. However, at the fixed end, the deflection and the slope is 0. All right. So now we know that the maximum slope will occur at the free end. Therefore, we can say that at the free end, where we see x equals 0, dy dx will be maximum. Okay, dy dx will be maximum. So what is it then? So EI dy dx maximum will be what? At s equals 0. So we will just have WL cubed over 6. Therefore, we can say that the maximum slope dy dx max. So dy dx maximum will be what? WL cubed over 6 EI. All right. So WL cubed over 6 EI. And that is the maximum slope. Okay. So maximum slope. All right. And then for the let's look at the deflection. Okay, so to get the deflection, we will have to integrate the slope. Now if I integrate the slope, I'll get eiy minus w over 6, put it at one side, then come to x cube. If you integrate x cube, you get x to the power 4 divided by 4 plus w over 6. If you integrate L cube, it's going to be L. Oh, sorry. L cube is a constant. It's not a variable in X. So that's all. Plus C2. Okay. Again, what did we say? We said that at X equals L, Y is 0. So let's move forward. So at X equals L, Y will be 0. So 0 equals minus W over 6, L over 4, plus W over 6, L cube multiplied by what? L over 4. Oh, sorry. Let me go again. Let me do that again. So 0 is equal to minus W over 6 multiplied by L to the power 4 divided by 4. Because it is x4, so it's going to be L to the power 4. Plus W over 6, L cube multiplied by x, so it's going to be L4, right? Plus what? C2. All right. Then now from here, we need to solve for C2. So C2 will be what? When we bring this one here, it's going to be positive L to the power 4 over 24. Then when we bring this one here, it's going to be negative L to the power 4. And what is that? So we are having some things in common. So we'll factorize them out. And then let's solve for C2. So solving for C2 will be what? Sorry about that. So C2 will be 1 divided by 24. So minus 1 divided by 6. So minus 1 over 8. So minus WL4 over 8. That is C2. So we'll go back into the equation and then we will solve for C2. So it's going to be x4. 6 multiplied by 4 is 24 plus W over 6 L cube X minus WL4 divided by 8. That is the C2. All right. So at this juncture, I think we are good to go. But then let's so this is the deflection equation. Let's find the maximum deflection. Let's find the maximum deflection. Okay. So to find the maximum deflection, you can see that at x equals 0, y equals what? Y max. That's what we said. We said that for cantilever beam, the maximum deflection will occur at the free end. Okay. So you have to go straight forward. And then you see that EI, Y max. So 0 plus 0 minus W L 4. Okay, because everything there will be 0 over 8. Meaning that for a cantilever beam with a uniform distributed load, the maximum deflection is going to minus WL4 8 EI. And then that is it. So that is the maximum deflection for a cantilever beam. All right. So we've been able to solve for the slope and then the deflection. Thank you very much for watching.